So famously, after George Romanes wrote his book, Lloyd Morgan, who was a psychologist, an early psychologist in the 19th century, in the 20th century, he wrote a book called An Introduction to Comparative Psychology, and it was the first book of comparative psychology. And having observed his dog, which is interesting that it was his dog that really influenced his writing, he observed that his dog had some complex behavior when it came to opening doors, that he was able to open the latch of a gate, push the gate open, and go run around in the neighborhood as he pleased. And he had many friends comment, and even for himself, he wondered, what was it that allowed the dog to do that seemingly complicated behavior? So he watched a number of dogs, including his own dog, solve new problems trying to open gates and leave the enclosure that they were in. And what he observed was that it's not that the dog actually understood that the gate latch was connected to the actual gate itself, and that connection had to be broken. It seemed instead that Lloyd Morgan's dog really had to practice and had to make a lot of mistakes, and slowly was able to shape their behavior and develop a set of motor patterns that allowed them to open that gate successfully repeatedly. So what he concluded was a behavior that was seemingly intelligent. And in the case of humans, it would be that you understand, hey, that's connected, I've got to disconnect it in order to open the gate. But that was not the underlying psychological mechanism in his dog. His dog was using practice and making lots of mistakes, trial and error learning, or associative learning, to learn a motor pattern that was successful. And so in his book, Introduction to Comparative Psychology, he famously stated Morgan's canon, which is similar to Occam's razor in biology, which is, in no case may we interpret an action as the outcome of the exercise of a higher cyclical faculty or psychological ability if it can be interpreted as the outcome of the exercise of one which stands lower in the psychological scale. So the terminology is a little bit dated, but the point is that we have to favor more parsimonious or simpler explanations for behavior until we can rule out that simple cognitive mechanisms or internal processes are allowing animals to do what they're doing. When we can rule those parsimonious explanations out, we might think about more complicated mechanisms, but unless we can rule them out, we should always assume that it's something simpler that's driving an animal's behavior. That was his idea. If we were to really understand animals, we have to avoid attributing human characteristics and really think of what are the simple mechanisms that could be driving or be the internal process allowing an animal to solve any one problem. Okay, so this is one of my favorite examples of exactly what Morgan was talking about. This is an experiment that was conducted by Elisabeth Elvisabergi, and it's a depiction, obviously, an illustration. And what we have here is a trap tube. You see that there's a PVC pipe, and inside there's a red arrow pointing to a peanut, and there's a capuchin monkey that would really, really like to get the peanut out, and the capuchin monkey has to use the stick to push the peanut out of the tube. Now, the trick is that in the middle of the tube, there's actually a trap. You can see in the middle of the tube, there is a little container underneath it. And if the capuchin monkey were to push the peanut towards that trap in the tube, the peanut would actually fall in the trap and the monkey couldn't get the peanut anymore. So of course the monkey wants to avoid doing this. So Elisabeth of Elvisabergi was very interested in the mechanism that capuchin monkeys use to solve complex problems like this. How do they use tools, and how do they understand their use of tools? Do they really understand the causal property that the tool can be used to push a peanut away from a trap, that if a peanut goes near it, gravity will pull it into the trap? And so if they really understand gravity and they understand how tools function causally, they should do exactly what's depicted in this picture. They should always put the tool in the end of the tube that is farthest from the peanut and push the tool through the PVC pipe so that the peanut falls out the other end, and not go to the end of the tube closest to the peanut, because of course that ends up with the peanut in the trap. Okay. So what she saw was that monkeys could solve this problem, at least some of them. But the interesting thing was, like Morgan's dog, It took a lot of practice, a lot of trial and error, and eventually some of the monkeys became very proficient at this. Now, you could conclude one of two things from the fact that the monkey could solve this problem. The monkey solved the problem, and like me and you, even though it took a lot of practice and a lot of trial and error, they now understand it. And it's not like in class or school I understood everything for the first time. Whenever I did it, I had to do a lot of practice, with long division or multiplication or calculus, whatever it was. There was a lot of practice involved, and after I practiced, then I understood. So it could be that that's what's going on with the monkey. Alternatively, it could be that through trial and error, like Morgan's dog, the monkeys have learned a simple motor pattern, and they don't really understand gravity, and they don't really understand anything about what that tool is really doing. So how would you test it? So this is your challenge of the day. How would you test between those two hypotheses? One is that the monkey has a very sophisticated understanding. The other is, it's trial and error learning. They don't really get it, but they've learned a strategy that in this one context works. They're not going to be able to generalize it to a slightly different situation. So how would you do it? What's the experiment that you could do to test between those two things? Well, one hypothesis has the prediction that if you slightly change the situation, the monkey should be able to solve the problem. The other hypothesis is that they won't. So I'm going to give you a second to think about this. I'm stalling a little bit so you can come up with what you might do, because it's a brilliant experiment. It's very simple. Okay, so what did Elizabeth of Visselbergy do? Well, she inverted the tube. And by inverting the tube, now the trap is no longer functional, but it's still there. And what she did is she gave her very best monkeys this problem again. And the question was, do they still use the motor pattern and the strategy that they had through trial and error learned, or because they understand that now the trap tube is totally not functional anymore, that they can use a new strategy? And what she saw was that the monkeys continued to successfully get the peanut out of the tube, but they used the same strategy that they did in the previous situation when the tube was functional. They would insert the stick or the tool in the end of the tube farthest away from the peanut, and they did that systematically, even though the trap was no longer functional. And the prediction was, of course, if they had a really clear understanding of the problem, like you and I do, well, they're not going to continue to use that strategy. They're just going to push whatever side they want to get the peanut fastest. So she concluded from this that while they can learn to solve the problem through trial and error and form an association between what end of the tube they need to put the tool in, that they don't really understand the causal properties of gravity, of how the tool is actually pushing the peanut. And so in this way, attributing human capabilities to the monkey would be erroneous. It would be wrong, and it's the wrong psychological mechanism to explain this behavior with. So that's an example where an experiment, an elegant experiment, was able to tease apart two different potential hypotheses or explanations for a pretty complicated behavior.